If you were in a Gen Chem like 151 class, theoretically you were told to memorize this. Your strong acids, and then recognize that your weak acids were anything other than that. Okay? If you were in Chem 130, you probably weren't told to memorize it. For my class, I probably said, this is a good idea, but I'm not going to make you do it because you're not going to see any questions specifically on it. Okay? But it's important because when we want to identify our definitions of acids and bases, if you've memorized HCl is a strong acid, well, it's in its name, it's an acid. You can just draw out it as a chemical reaction to say, well, what is it doing through the course of this reaction? And it can help you derive those definitions, which is what we just spent 20 minutes trying to go through and do. Okay? The next part comes in with weak acids. Okay? Well, the weak acids, what we're trying to do is figure out, okay, whether they're strong or weak, or stronger or weaker. And even with our strong acids, we can do the same thing. We can go through and we could compare HBr to HCl, and we could say which one is a strongest acid. Well, how? If they're strong acids, what happens? They produce H+ in both scenarios, and then they would produce the conjugate base. And if we're talking about stronger, what we're saying is we get more of the H+ in one scenario versus the other. Okay? Which is ultimately saying that if we look at these as equilibrium reactions, they could go forwards and backwards, that one of these reactions can go backwards just a little bit more than the other. Well, why? How could we possibly predict that? Well, predicting that has to do with knowing what you should be evaluating first as you process through a reaction. Okay? And the challenge behind that is knowing what to look at. Okay? So when you go through and look at this chemical reaction or chemical reactions, what stands out to you? What makes you go, that's dangerous, I don't want to look at that? Well, that's bad. It's a hard question. So we'll push on a little bit more. In Unit 1, we talked about Lewis structure. And when drawing out Lewis structures, so here we officially have 6 Lewis structures. We've got HBr, H+, Br-, right? 6 Lewis structures. When looking at Lewis structures, what's the number one thing that we need to fix? Octet rule. Okay? So when we look at these 6 things, we should immediately jump all over missing octets. Do we have any missing octets? Yeah, where are we missing octets? Try again. You were right. I screwed up. Come back to charge. That's an important one, but that's actually the next step. How many electrons should be around a hydrogen? What is hydrogen's octet? Hydrogen comes in with 1 valence electron. What's hydrogen's octet? How many electrons should you draw around a hydrogen? Is it 8? It's not 8 because it's missing a whole bunch of electrons. It's 2. Does this hydrogen have 2 electrons? Does this hydrogen? No. So that should be a giant red flag. This hydrogen is missing its octet on the product side. Okay? This is a problem, we need to fix this. Except, is it a problem we should be addressing? What happened with the other one? Exact same thing. So yes, as an octet, that is a big issue, and I don't like missing an octet, but it's the exact same destabilizing factor for both equations. And if it's the same, can I use that to evaluate which one is stronger or weaker? Nope. Right? Which means I won't look at H+. What comes after the octet when trying to establish whether we have a good structure or not? Charge. So we could now go through and look for charges. Yes, we could evaluate the hydrogens, but we just went through and said that those aren't different, so we're not going to evaluate those. And instead what we can look at is our chloride and our bromide. And we want to decide which of those is more or less stable. Okay, so how do we do that? Well, the first place we should look is exactly what you suggested, the charge. Is there a difference in charge between them? Nope. Okay. What's the next thing you should evaluate? Okay, and if you're like, I don't really know, that's probably because you didn't watch or understand the video on reactivity, okay, or the reactivity of things, because that's what we use to evaluate. Electronegativity is on that list. Unfortunately, it's not first on the list. It's size. It's not mass, it's size. Okay? And why is it not mass? What we're concerned about is the charge, ultimately the electrons. The electrons aren't contributing to the overall mass. What we care about is where those electrons are located. Okay? And if we compare bromine to chlorine, is there a difference in size?
Yes.
Yeah. What's that difference?
Like,
Try the other way. Bromide is significantly larger. Okay? So if we look at bromide, that electron has this space to occupy. That extra electron that's making that charge. If we look at chloride, this is not drawn to scale for the record. Okay? That electron has that space to occupy. Which of those is more stable?
the big one?
Why? That's a really hard question for the record. I would really just push to analogies.
Like you stand, if you like you bigger, you stand more stable.
So the way I would consider this, if we consider reactivity, for this to react, the electrons must touch something else. Okay? So let's say if it connects, we get a reaction. Okay? So let's say the electron is like a cattle prod. You must stick your hand into one of these circles. Which one do you stick your hand into? Why? Which ultimately means when I stick my hand into the larger one, the odds of me actually hitting that electron are less. And if it doesn't connect with it, I don't get a chemical reaction, which means bromide is more stable than chloride. Why is that important? If we're talking about this reaction going forwards or backwards, because bromide is more stable, chloride is more likely to encounter the H+ and go backwards than the bromide is. And if it does so, what happens to the amount of H+? If chloride reacts with H+ to make HCl, do I have the H+ anymore? Nope. So what happens to the amount of H+? It decreases. And if it decreases, there's less protons to donate. What does that mean? HBr is now the stronger acid than HCl. When can I use this comparison? All the time. I can use it for my strong acids, okay? But ultimately for the strong acids, we care less about those because we just say they fully ionize and we don't worry about it. But we can use it a lot for our weak acids. And it can allow us to predict whether we put a hydrogen on or off of a structure based off of just, well, does it make a more stable product? Yeah, okay, let's do that. Okay. Does it make the product more unstable? Oh, let's not do that. And so it sets you up with this scenario to always be comparing and saying, well, what if? Okay? And that is very challenging for students to deal with, because ultimately what it means is that you have to what if everything. And that also means probably 60% of the time, your what ifs are going to result in dead ends. You're going to be like, oh, this was useless. This didn't produce what I wanted it. That's not useless. That is exceptionally powerful and useful, because you now know what doesn't work. Okay? And why is it useful to do that in the homework? Because when you get to the exam, you won't be spending your time checking all the what ifs, and you will check the exact correct answer right out of the gate. But it requires that you do the practice in the homework, finding your what ifs. And that is very, very difficult for everybody to deal with, because how often do we like just going through and attempting something and failing at it? Right? But that's what you need to go through and do. And so when we talk about our acids, we're talking about stability. We've got a ranking of things that we should be looking at. We start with charge, size, electronegativity. We can move to molecular effects after that. The molecular effect of size is resonance. Can you move the electrons around? Molecular effects, electronegativity. Is there an atom somewhere in the molecule pulling on electrons? Okay, that's going to change the reactivity. And so what you are trying to do is match the definitions of those chemistries, acid, base, nucleophile, electrophile, to those characteristics, allowing you to go through and create mini rankings that allow you to then go through and predict reactions. Okay? When are you going to have to do that? For the most part, you're going to be doing it with acids and bases this unit. The rest of the units, you'll be doing it with everything. Everything you touch will be evaluated with the why should this happen? And it'll come back to one of these rules. Okay? This can also be done without rules, and I really want to get through the last of this. Instead of looking at rules, you could go through and you could quantify things. You could go through and use equilibria. Again, Chem 130 should have mentioned this. We've got equilibria with products over reactants. Okay? And then what wasn't pushed in Chem 130 is that you can now start to really quantify this and push this and go into really crazy systems, and you could now rank the ability for an individual molecule to act as an acid. Okay? The results you're going to get out of that are powers of 10. How many people liked powers of 10? You didn't, okay? Most people don't, including scientists, so they converted powers of 10 into pKa's. pKa's got rid of the powers of 10, but it also inverts the scale. You heard of pHs? Okay, what does a low pH mean? Acidic, and a high pH means basic. Okay? Your pKa's are ultimately doing something very, very similar. Okay? A small value, small pH, results in a very strong acid. Okay? A bigger value results in a weaker acid. The pH scale runs from 0 to 14. Your pKa scale runs from 0 to 60. Why so much larger? pH is based on water. Water only can support so much differential in ions. As soon as we shift out into organic, we can shift these things way further out there. Okay? So if we go through it and push all of those, what we can end up doing is memorizing these pKa's and then taking a next step and go through for individual functional groups, memorize their pKa's. If you've got those pKa's memorized, you don't have to do as much of this work, because the pKa is the answer. This work is, why is that the answer? Okay? Even if you memorize pKa's, you must still apply them, and that does become a challenge. Okay? Are these pKa's particularly relevant for all of you? Yeah. Which one's the most relevant? Carboxylic acid, alcohol, The amine, which is of course a nasty one, the 9 is the one you want on your amine, and probably your phenols. What do those 3 functional groups all, or 4, 1, 2, 3, 4 functional groups all have in common? Their pKa's are lower than 14. Where do they all show up? Biological systems. You will see carboxylic acids, alcohols, the amine with the pK of 9, and your phenol will all show up in biological systems. So when we talk about how bodies process things, they're processing things using those functional groups. And so if you knew those functional group pKa's, it can allow you to explain why certain things are happening within the body.
You said lower than 14, alcohol's 15. Is it like an exception for the same batch or something?
Alcohol with 15 ultimately is right at the end of that scale. It's the same as water. Comes in at 15.7. It's pretty much the max. So you're not actually going to see it do much, but that functional group shows up a lot. And ultimately what you would have to memorize is that it doesn't do anything. So it's a little bit of a weird one to include in this list. As a functional group, it shows up a lot. It actually doing anything with transferring the hydrogen, slim to none. Okay. But if we look at the alkanes at 50, so far outside that scale, it doesn't do anything. Okay. The alkene, same deal, alkyne. The amine, where you've got to get real careful, is that 35 one. Okay. And that's talking about different protonation states for amines. Nitrogen's nasty. You can do a couple different things that mess with you. Okay. So, acids and bases. What we're going to start with on Wednesday, is we'll pick a couple acid-base reactions, look at how they would react and what that means as far as an energy diagram. So you can do a basic interpretation of an energy diagram, and then we'll start actually nitpicking some kind of mechanistic details. Okay, those mechanistic details are probably a challenge, but that's, I think, the video that you were supposed to watch this week, if not next week, elementary mechanistic reactions. Okay, for the most part, that is, can you recognize what happens? That's it. You don't need to know why, you just need to know that it happens and what it's called. Okay? And I apologize, I'm stopping.